Alright, so now we're in the EA3 directory. This was an attempt to evolve a system that could detect two different frequencies and discriminate between them. And as described in the first video, changing every 4 cycles should produce an output of 0. Changing every 4 ticks. Changing every 8 ticks should give you an output of 1. So we're doing simple frequency discrimination. So this system ran and saved its raw output, and in this case a perfect score is 8,192 because we required it to do perfect output for 64 consecutive clock ticks, and we only had 2 tests, input of 0 and an input of 1. So let's go ahead and analyze this. So set up our windows, we'll open up a live view, and let's expand this live view a little bit. Let's zoom in. So we'll say file raw. That was our raw data file. And in this case, it was individual 181 from generation 25. And that achieved a perfect score of 8192. So if we say test 0, this is the higher frequency system. And it should output a 0. The code right now is set up to do a more extensive test. So here's what I'm going to do. I'm going to slow this down to 200 milliseconds per tick. And I'm going to run test 0. So we're going to see the input in this region and the output in this region. And the first 64 ticks are going to be set up, and then the next 64 will be scored, and we'll see the output. And then I'll go ahead and set the delay to 0. And we'll ignore the remaining output. So let's run test 0. And you see the input going high for 4 and low for 4. And the output is starting to develop. And we want to see a 0 in this region. So starting at tick 64, which is right now, it'll record the output throughout this region. And we see it's a nice steady 0. And this should go all the way up to tick 128. And that's as far as the system was required to respond. We run an additional almost 1,000 ticks, and if I bring the delay down to 0, you'll see that the system starts to misbehave at this point, and eventually it outputs 1s, and the whole thing saturates. Alright, so let's put our delay back to 2,000, let's reload our circuit, and this time let's run test 1. And now you see the system goes high for 8 ticks, and then low for 8 ticks, and then high and low. And we want the output to be 1 by tick 64, and you can see that's happening now. This area has been filled in, and now at tick 64, the output's a nice solid 1. And that'll persist through tick 128, which again, this circuit was only supposed to work for the next 64 ticks, so 64 through 128. The test that I'm running is different code, so it actually continues testing it, but that's outside what the circuit was required to do. So let me set the delay back to 0 and spin through the remainder of the tests. So this is a system that can actually differentiate, and we can see a little clearer what's going on if we load it in. Let's set a delay of 1,000, and let's run test 0. So our input is over here, and it goes low for 4 ticks, and then high for 4 ticks, and low for 4, and high for 4. And you can see the input over in this region near our scan line, and you can see the output developing here. So let me speed this system up a little. We'll put the delay down to 200. And here's our input changing. Here's our
the time is
output responding.
1200 hours.
And there's the time. Alright, so put this back to a delay of 0, but you see what the frequency is here on this input. And then let's load it and do test 1. And you'll see that it basically uses half the frequency, so twice the period. Let me speed this up. So it's basically a system that's going to respond to either this higher frequency or this lower frequency. and try to generate the correct output. So this is working fine for a system that's supposed to be correct for 64 ticks. So the system that's running right now is trying to evolve a system that will be stable for 1,000 ticks after the first 64. And that's getting pretty close. We're still in generation 1 because I killed this as it was running. But it started over, and I will do another video once I get some results from this test.